no solamente se pueda pues llevar como charlas y hackatones y todo eso, sino también como concretar en acciones muy, muy buenas y en talleres. Para ello les voy a compartir un videito que es muy corto, pero muy útil para nosotros.
FERLAC Jalisco es una iniciativa liderada por el Banco Interamericano de Desarrollo, el Tecnológico de Monterrey en Guadalajara, el Gobierno de Jalisco y C-Minds. FERLAC Jalisco trabaja a través de la articulación de academia, sociedad civil, sector público y sector privado en 3 componentes. 1. Es la implementación de soluciones tecnológicas mediante técnicas de inteligencia artificial para resolver problemáticas sociales en Jalisco. Otro es la recomendación en creación de política pública para el uso de inteligencia artificial, así como el impulso del uso ético y responsable de esta. Y el tercer componente es el fortalecimiento del ecosistema emprendedor local de inteligencia artificial responsable. FERLAC Jalisco forma parte de uno de los hubs de FERLAC que tienen presencia en Medellín, Colombia, Costa Rica y Uruguay. En Jalisco se cuenta con un diferenciador único, el componente de emprendimiento que busca fortalecer al ecosistema emprendedor en IA a través de actividades como el programa de aceleración de startups de IA PASIA, IA Talks, talleres de integración de inteligencia artificial responsable y de Venture Capital, hackatones y el análisis del ecosistema jalisciense de emprendimiento en inteligencia artificial. FERLAC, por un uso ético y responsable de la inteligencia artificial.
Bueno, y pues para abrir este espacio me gustaría darle la palabra a nuestros talleristas, estrellas en esta ocasión, que son Madi, Jaime y Edgar. Muchísimas gracias por este espacio. Les recuerdo a los asistentes que pueden hacer sus preguntas. Bueno, igual ahorita Madi nos va a explicar mejor la dinámica. Va a ser en inglés. Y cualquier duda también estamos por aquí en el chat. Mi nombre es Fabi Velarde y si tienen alguna pregunta o algo en lo que les pueda apoyar, el chat también puedo estar por ahí apoyando. Madi, Jaime, Edgar, el micrófono es todo suyo.
Ok, muchas gracias, Fabi. ¿Me escuchan? ¿Sí?
Sí.
Ok.
Sí.
Ok, gracias. Okay, hello and very good afternoon, everyone. Welcome to the Adversarial Machine Learning Stand-on Experience. I think I hear some noise. I think, oh, okay, perfect. Okay, thank you. So this workshop is delivered by Edgar Lone Sandoval, Jaime Zuniga Mejia, and me, Mahdi Zarei. First and foremost, who contributed most to this workshop, Edgar Lone Sandoval. Edgar is a PhD student at Technologico de Monterrey. I want to give you a brief introduction about who we are, then we start with the workshop. Edgar is a PhD student at Technologico de Monterrey, pursuing degree in the computer science program with emphasis in natural language processing for sentiment analysis. He holds a master in information technology from Guadalajara University, and he used to be software developer engineer at Amazon, a big data engineer at EPAM, and R&D engineer at Intel Corporation, doing mostly software development in massive parallel system using GPU, Hadoop, and microservice architectures. Dr. Jaime is a postdoctoral researcher at Technologico de Monterrey in a telecommunication research group. He received his mechatronic engineering degree from Tech in 2013 and PhD in telecommunication in 2019. And his research is focusing on mainly security in reconfigurable networks and also wireless channel modeling. And last, I'm Mahdi. I'm a research professor at Tech Campus Guadalajara. I joined Tech in 2017 as a postdoctoral researcher, working in telecommunication research group, and from 2019 I'm working at Campus Guadalajara as a research professor. And my research also is mainly concentrated on telecommunication, IoT, 5G, cybersecurity, and also applied machine learning. So I believe those who are registered to this workshop, they have already seen this image. Actually, this is just requirements For the workshop, I mean, I hope most of you already have some basic knowledge on machine learnings and a little bit knowledge on Python and Jupyter Notebook. So if you have those conditions, you're gonna get the most out of this workshop. Anyway, I'm going to share the basically slide links with everyone so you can also have it. Okay, so it's in the chat. You can take a look at it. So this is the outline of today. First, I'm going to give you a very brief introductions and talking to you what is the big deal and why we need to talk about it actually, and giving you some example of basically adversarial examples, machine learning. Later on, Dr. Jaime will follow with how to make those attacks, explain more about how to perform those attacks and also how to defend them. And last, Edgar going to walk through code so you can have basically a hands-on experience, and then we finish the session by taking some questions and trying to answer them. So I'm pretty sure basically most of you already know AI and machine learnings are already part of our daily lives, okay, and no more in the realm of science fiction. For example, computer vision has become present in our society with application in image understanding, mapping, I don't know, you name it, medical, in medicines, self-driving cars, drone. So visual recognition tasks like image classification, localization, and detections is the core to many of those applications. The recent development in neural network or deep learning approaches have greatly advanced the performance of those visual recognition systems. It's been said from 2014, machine learning performance surpassed human performance in basically in visual recognitions. So however, AI and machine learning applications are not limited just to image recognitions, as you well know. When you use your voice to unlock your phone, when you use your voice when you talk to Alexa or ask certain information from Siri or basically Google Assistant, you're using a speech recognition. You don't receive nowadays a massive amount of spam emails in your inbox because of a statistical inference done by machine learning algorithm when you receive emails. It's easier more than ever for the banks, for example, to detect fraudulent activities, for us to predict weathers, to have better medical diagnostic, and so on. So, and if you quickly search about it, you can find tons of different applications. For example, the last one I wanted to particularly mention is a project done under the Fairlake Jalisco, and I invite you to get to know more about it. So AI and machine learnings are already part of the life, so it's very important to talk about the security aspect of it. And of course, they're going to be even playing a more important role in the near futures. So what is adversarial attack? Adversarial machine learning is basically a study of machine learning vulnerabilities in adversarial environments. So those vulnerabilities in machine learning system can arise both from flawed system design or fundamental algorithmic limitations or combination of both. Later on then, Dr. Ahmed, actually he's going to explain with details how we exploit those vulnerabilities and how to defend against those. But for now, let's talk about some of the examples. So if I ask you what you see in the basically left image, most probably the answer would be a panda, right? But if I ask you what you see in the right image, most probably you're gonna wonder why I'm asking that 2 times, because it's the same image, so this is also a panda. But when we basically give these 2 images to convolutional neural network, machine tells you the right image actually is a given with 93%, more than 99% confidence. Okay, and obviously you can see this is not a given, right? So just a minute ago I said computers surpass human performance in visual recognition. So what's happening here? So actually this is an example of adversarial. So adversarial examples are actually inputs to machine learning models that an attacker has intentionally designed to cause model to make mistakes. So basically, attackers attempt to fool machine learning models by supplying deceptive inputs. Okay. For example, in this case, we have the actual image, original image. We introduce some noise and perturbance in the actual image. The output image is not basically for us as a human being. We still we don't notice this noise, but we still see it as a panda. But when you give this to basically neural network, it tells you it's a gibbon. Okay. Actually, this is the source of this basically study was from Goodfellow. Actually, he mentioned some people start applying this particular noise that he introduced into their Facebook profile pictures, and actually they could fool Facebook facial recognitions. So you may think, actually, what a big deal about this, okay? Because here we are carefully engineering certain noise, okay, to fool the system. So it's not going to be such a big deal in actual application, for example, in autonomous vehicle, right? So if you're thinking like that, because there are researchers actually thinking, for example, we don't need to worry about adversarial examples in object detections, for example, in autonomous vehicles. And what they were basically arguing is they were saying because the cars get basically the angle of the camera with the object that is trying to detect is constantly changing because of the car is constantly moving. So we're not going to have those type of problems in, for example, autonomous vehicles. So some other basically researchers start working on that. In this study, for example, done in 2017, what they did actually, they get some image, okay, they printed out in the piece of paper. So you can see this is actual image without any noise or perturbance. And as you can see, basically the algorithm can correctly detect it as a washer. But when they introduce actually the noise to the actual image, and then they print it in a piece of papers, then actually they could fool the algorithm to detect it as a loudspeakers. So actually this study shows those basically adversarial attacks can actually happen in physical world, okay? As you can see, for example, in this video, it shows that the printed basically adversarial pictures also can be misclassified by the algorithm. So it's not just about the how to say digital image, as you can see here, for example. So again, some people might argue, okay, this is still a 2D image, not going to be a big deal in a 3D world, okay? So some other basically researchers start working on that. In this particular study, they did a 3D printing, they 3D printed a turtle, okay? And then basically they put that turtle moving in front of the camera from different angles, different perspectives. And most of the time, as you can see in these pictures, most of the time is misclassified as a rifle. Only in this particular angle is classified as a turtle. So this video shows basically how they were working. So as you can see, it's changing the direction of the turtles, the angles of the camera still is misclassified most of the time as a rifle. So actually this shows that it's not just limited to the digital image, not just limited to 2D images, it can be actually a big problem even in the 3D world. So why does it matter? I mean, after talking about that, showing you that it can affect really all sorts of basically applications, 2D, 3D, everything, okay. And now that you know, basically AI and machine learning algorithms are becoming bigger part of our daily life, like for example, in autonomous vehicles, in drones, in law enforcement, right? Even there are basically researchers working on pornographic detections in different videos using AIs to basically protect the child, to provide better basically child contents, to make it automatic basically detection. So actually it's important to discuss, and for example, there are some examples here that what if it goes wrong, it can really cause serious problems. So here I want to talk in the next few slides, some examples of it, okay, why we need really to know it, why we need to consider it, and why we need to basically study it. So the first example shows autonomous vehicles. This is basically what Tesla autopilot sees on the road, as I title suggests. As you can see, basically the car is driving, it's detecting the stop sign. So the car slowing down and stopping, it's going on the road, detecting light, all sort of basically street signs, right? And performing the actions according to those speed signs. But in 2018, researchers shows that they can actually modify the speed sign and spool an autonomous vehicles, okay, in order to make it, for example, so autonomous vehicle look at this stop sign and thinks, oh, it's for example, the speed limit to 45 kilometers per hour, or it's unlimited speed limits. Because, for example, the issue with this actually is, for example, this picture here is taken from an actual street. It's just a normal stop sign that you can find in any street. There's some graphic on it, there's some colors, some stickers, okay? So maybe if you see this also in the real street, you may not even notice that actually this is an adversarial attack. You think, oh, just this normal stop sign losing some colors here and there. But this is actually an adversarial attack. So it's a very serious issue and need to be considered. Or in another example, for example, here you can see in 2016, researchers were able to fool a commercial facial recognition systems into thinking they were basically someone else, just by wearing a pair of pattern glasses. So basically, they put this funny-looking glasses, and they could basically all the time they get misclassified. For example, this time the algorithm classified these researchers as Mia Djokovic, American actress. And in the other picture, you can see, for example, how they can fool person detection algorithms by just having basically one picture here, right? In order to fool the algorithms not to detecting this as a person. So it can have different, basically, those basically adversarial examples can be introduced into different sort of applications. Now you can see it's passing this one, and now this other person cannot be detected as a human, as a person. So actually, I just find this interesting to talk about. Actually, as you can see, it's like they are actually start commercializing these type of things. For example, it's adversarial anti-facial recognition, invisibility t-shirts. So basically you print this on your t-shirt, and most of the algorithm most probably going to be fooled and not be able to detect, for example, your face. If you, for example, upload this type of photo, take a photo with this t-shirt, upload it in a Facebook, most probably they're not going to be basically detecting your face. So the thing is actually, so whatever so far I discussed is mostly there were like image processing world, but it's not just adversarial attack is not just limited to image processing. So here I want to play a very 1 minute video about adversarial attack in voice recognitions. So what they do actually, they play a small 2 second, 3 second voice for you, the one you can hear, and then what a machine interpret that voice. So please listen to this.
So I'm going to play some audio that you heard before, and this is going to be a transcription.
Most of them were staring quietly at the big table.
Okay, so that's the baseline audio that I'm going to work with for basically the rest of this talk. So now let me play you the adversarial version.
Most of them were staring quietly at the big table.
Okay, so first of all, could you tell it was perturbed? Maybe. You could hear a little bit of clicking. I would say that you can probably only hear that because you're listening for it right now. Turns out the first audio sample I played for all of you was the adversarial one. So when you're not really listening for it, it really is very, very subtle. But if you are listening actively for it, you can sort of hear a little bit clicking in the background. Okay, so what does this actually recognize as? I mean, so it's hard to hear the perturbation, very hard to know what it recognizes as. This recognizes as the full sentence, it was the best of worlds, it was the best of times, it was the worst of times, it was the age of wisdom, it was the age of foolishness, it was the epoch of belief, it was the epoch of incredulity. So that was that 5-word sentence recognizes this complete thing, which is clearly wrong, if only because this is way too long to have been occurring in that 2 second clip.
So you can see it's adversarial attacks can be applied to even voice recognition. It's not just about image recognitions. So And it's not just limited to voice and image. It can even apply to sentiment analysis. As you know, aggregating and basically crunching users' opinion and reviews about services, places, products can generate actually a lot of value for several companies like Amazon, Booking.com, or so on. Okay, so even if there can happen attacks on sentiment analysis like the one that you can see in this particular papers. What they did actually, they got this movie review, and by changing just 5 words in that movie review, they basically fooled basically the algorithms to detect the original text is, as you can see, is detected as negative with 78% confidence, and basically adversarial text is detected as a positive feedback on that movie with 60% confidence. So you can see it can be applied to different basically applications, different ways. So it's something serious to really consider. And it's not just limited to those. You just do a quick research and you can find tons of other research done in this area. Before just finishing my talk and going to Dr. Jaime to get more technical detail, I also wanted to talk about adversarial emphasis examples in the human brain. If you look at this particular picture here, okay, so you may think it's a spiral, okay? But actually, these are not basically spirals. They are concentric circles, okay, if you pay attention. But what's happening, this tilt is this basically a tilt in the edge of these squares are somehow messing with our edge detectors in our brain. So it's fooling us to see it as a intertwined basically lines. But it's actually basically concentrated circles. So I passed the stage actually to Dr. Jaime to continue from here.
Thank you, Mary. Let me share my screen.
Go ahead.
Can you see that slide?
Yes. Yes.
Okay. Great. Hello, everyone. I'm Jaime. I'm trying to explain in an intuitive manner what is going on with those machine learning models and what is a possible explanation for those really weird adversarial attacks that Dr. Mandy was telling us about. In order to do that, I will take a few steps back, and I would like to explain the intuition behind how these models work. And I want to start with an explanation of the classification problem with a little example. Let's say, for example, that you have been working all day and suddenly you feel a little bit hungry, you want some snacks. So you walk to your closest vending machine to get some cookies or whatever you like. Well, this vending machine, each time that receives a coin, it's solving a classification problem, in the sense that it takes some, or what a classification problem means is it's taking as an input a set of features. In this case, could be measurable features of that coin, as could be, for example, the size of the coin, the conductivity as a property of maybe different coins are made of different alloys and have different electrical properties, etc. Could be differences in colors, for example. And the goal of the machine is to determine if this is, what is the value of that coin from a set of known values, right? Could be 1 peso to peso 5, 10, 20, maybe 50 cents or whatever, but this is the main idea. You have a set of measurable features of the object of interest. And then given those measurements of those features, the algorithm has to predict an output label. In this case, value of the coin. Okay, the next concept that I want to explain is what is called the feature space representation. This is a graphical representation of what I was just talking about the properties or the features that define the object, in this case, a coin. As I have said, those features need to be measurable. So each value of an instance of a coin could be placed on a numerical Euclidean space, Euclidean plane, as this one, for example. If we are considering, for example, for the coins examples, just two features, size and conductivity. And every time that we put a coin in the machine, we can represent that coin with that particular size and conductivity values as a point that is represented in this plane. So different coin values will form different, you can think about them as clusters. I'm showing here in blue, for example, this could represent the 5 peso coin, and in orange, the 10 peso coin, just as an example. Well, the next concept is the classification models. Classification models are basically a mathematical function that works as a mapping that takes those instances represented in the feature space that we were talking about, and it transforms that space through those mathematical functions into an output space. Please note that we are adding a third dimension or an extra dimension that represents the output probability that this particular coin belongs to a particular class. This abstract surface that we are seeing on the right side of the slide, well, represents that mathematical transformation or that mapping that I was talking about, and this is found by the training process of the algorithm. How does this training works? Basically, you have a particular architecture in your model, and this architecture has certain parameters that are trainable. In this case, this is represented with this W. The X represents the input signal, and the Y represents the output. And what we are using, the most common method to train a model is using the gradient descent method. So we define in the beginning, when the model is not trained at all, the output is just random noise. It's just producing, given an input, just a random output. So, but we have an output label of what should the model be predicting, because we're using label datasets, right? So we use that differences between what is producing as an output and what should it be producing to compute this cost function that needs to be optimized. And this is what we are seeing in this figure. That's basically, well, this gradient descent, what is doing is minimizing the prediction error in an iterative fashion, like taking little steps, modifying those model parameters a little bit at a time. So they are minimizing the prediction error. With that, we need to explain what are those limitations of the classification models. And I want you to think about it just as from the abstraction of the mathematics. As we were discussing, these neural networks or classification models are mathematical abstractions whose input signals, each one of these features in the feature space, are not really bounded, are defined for all the possible space, from the -infinity to the infinity values, right? I mean, we intuitively know that there are not, for example, negative values for the diameter of a coin, but the model is not aware of that. And what is happening is that when we are using a training set, given the fact that the training set is finite, we're just training a small region of that infinite possible feature space. So what happens when we have an already trained model and we input a signal that it's an instance that it's outside of the training region, we're most likely getting classification errors. And this fact is taking leverage by the adversarial attackers. And the idea here is really simple. We are taking an input signal. In this case, in this example, it's an image of a dog. We are adding some noise. For us, it seems like random noise. So it produces the image on the right side. But this noise is specifically engineered to fool the network. What it's causing this to do, the model, is that it's moving. You can think about the example of the real dog on the left as being inside the training region. So what it's the noise signal doing, it's moving that instance from inside the training region to the outside or maybe to the border of the region. This change is taken by little steps, so it's not visible for a human, but it's significant enough for the model to make mistakes. So there are several. This is just mathematically what we are doing when we are trying to find an adversarial attack. What we are doing is we leave the model parameters intact or fixed, and we are moving the input signal in such a way that we are increasing the classification error. In this way, we can classify those adversarial attacks into main classes. The first one is the white box attack. By white box attack, we mean that are those kinds of attacks in which the attacker knows the model parameters. The attacker may have access to the output probability vector of each one of the classes, of the output classes. Maybe the attacker has knowledge of the model architecture and the training methodology, and maybe the training data. This is not, these white box attacks are not very uncommon because the machine learning community tends to be really open and tends to share and open source a lot of these tools. So if you're using like open source tools and data sets, it's you might be targeted by a white box attack. The other kind of attack, it's called a black box attack. And by black box, we mean that, or I mean that the attacker has no knowledge about the model architecture, nor the training data, nor the training methodology, but it may or may not know something about the model parameters. In a few minutes, Edgar will walk us through a live demo, and we are using, we are obtaining an adversarial example for image classification by this method that is called fast gradient sign method. The idea here is really simple. This is a white box attack. This means that we already know the model architecture and maybe the parameters, but mostly we know the output vector. And what we are using is the cost function, the already known cost function, because we already know the model that we are using. And we are obtaining the gradient, so that that allow us to modify the input image to obtain an adversarial attack. And this is called the fast gradient sign method, because we don't care in this method, we don't care about the gradient value, we just care about the sign, and we multiply it by a small parameter. In this case, it's called epsilon, it's shown here. And this is very effective and really kind of easy to implement. Okay, so far we have covered a little bit about a basic intuition about why those classification models are susceptible to adversarial attacks, and how can those attacks be implemented. Next, what I want to discuss is how can we defend our models from these kinds of attacks. And there are mainly two classes. There's the first one is the reactive defense strategy. In this this scheme, or in this approach, what we're doing is basically we train our normal model, but in parallel we train a second model whose job is to detect if the input signal for example, in the case of the example of the dog, if this image is adversarial or not. This strategy tends to be effective, but it has a main drawback. And the main drawback is that it basically doubles your infrastructure needs, because you're training and you're implementing two models or two neural networks. A better, or yes, we can think about it as a better strategy is the proactive defense strategy. In this approach, the defense side uses well, first we add an additional output label that corresponds to an adversarial image or an adversarial input, and we train our model from scratch with regular or not adversarial examples and with adversarial examples. So in this way, what we are doing is training our single model or our single network to distinguish from regular or not adversarial from adversarial images or audio signals. An additional advantage of this strategy is that this process of using adversarial examples for the regular training of the model acts as a model regularizer, and actually it improves the classification performance on the real examples, and additionally helps us to defend against adversarial attacks. Still, it's not a silver bullet, but it sounds like a better option. Well, we should continue with Edgar live demo presentation. Thank you very much.
Thank you, Jaime. Can you guys see my screen?
Yes.
Yes.
Okay, so before we jump directly into the demo, I wanted to explain to you guys the setup that you need to do if you want to run them locally. And it is pretty simple. I did it in Linux. As you can see, my desktop is Linux. But these same steps should work with Windows or macOS or whatever you're using. The only difference will be that here we use apt to install Python. And if you are using Windows, you don't have that. But other than that, it's just as is. So here's the first part, here in line 6 to 8. is that we are creating a virtual environment within Python to kind of constrain the effects of all the stuff that we're installing. And this is a good practice in whatever form you choose to do. Either if you do virtual machines or Docker containers or whatever, because it gets messy to all the libraries. Sometimes they change APIs and they cause conflicts, and it's really painful to fix that. So I strongly advise that you guys use a sort of container, whatever you are gonna be using. This line 11 is just getting to our sources. It's just a single file, so no biggie there. And this from 14 going, it's the actual dependencies of a project. It's basically just TensorFlow and Jupyter. Keras, Matplotlib, that's required by TensorFlow. And here, just pay special attention to this H5 library, because that version is super old, but the newer versions just break in this example. And that's pretty much it. That's what you need to do. So you will activate your environment, and you know that it's activated because it tells you the name of the environment that you choose. And from there, you just run Jupyter, and it should launch your notebooks in your local browser, whatever that is. And when you're done, remember to kill your background service, and just deactivate your virtual environment so you run in your usual everyday environments. Right, so with that, if you guys have no doubts about this, I'm gonna jump into the first demo. And don't worry if you don't want to do all of that. We're gonna be running everything on Colab, so you don't need anything. This is just in case that you want to run locally. So we have two examples for you today. This first one is using TensorFlow.js. So all the code that I'm gonna show you next, it's exactly the same code that these guys are using. It's just giving us a nice JavaScript-based UI to play with it. So here, basically, you choose whatever data set that you want. I'm using Minist because it's pretty fast, because it's just digit recognitions. And here you get a data set like this, where it's just like handwritten characters. And the idea here is that we trained our model to get what this number is. So here the model is saying this is a 2, and I'm almost 100% sure that it's a 2. Right, so we can ask him on this side what number we want to generate. Let's do a 7. And first gradient stuff. And you can see that it's pretty much the same image, a little bit noisier, but we can see that it's still a 2. And here on real life, since this guy doesn't have an idea of the trainings, we're still predicting 2s. So this is pretty common in the real world. So it's not as bad as it seems. But then again, we have some fancier way to introduce noise. And eventually it tells you, hey, it's 7. And yeah, we can clearly see that this is just plain wrong, right? And this is very, 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 very important, because we use character recognition a lot in real life, and all of them are trained using MNIST, or most of them are trained using MNIST. So for example, if you get a automatic ticket, a speeding ticket, you might get a ticket and it's not even your car, and it's because some guy has something like this in its license plate, and it just changes one number and he doesn't get the tickets anymore, you get them. Or maybe you're trying to cash a check and the system thinks that a number is not what it is, and you get less money or whatever, right? So can get pretty scary. And this example is open source. So you can just go to the GitHub and they have the code for everything. So do that. But our main demo is this one. It's a example of adversarial image classification. This is exactly the same file that I put you into setup. Here, the only difference is that it's running on Google Cloud. And here you can see that it's consuming your resources. So you don't even need a dev account to use this. But Google does have a cap on what stuff you can use for free. So if you are playing a lot with this, eventually you are gonna hit your monthly cap and you can't run them for free anymore. And if that happens, they will just stop working. And if they stop working, you can also connect this to a local execution environment. So your local Jupyter environment that is already running, and you can run it from there. So here we have specifically an example of the fast gradient sign method that Jaime was talking us. So here, like he mentioned, this is a white box type of attack. I know that white box sounds like something unlikely to happen in real life, but the truth is that it's easier than it seems. If you do your threat models around your machine learning system, most companies will publish a white paper on what the technology they're using. And in there, you will find details on your models. So you can do pretty educated guess on what they're using. And sometimes they tell you exactly what architecture they're using. So what usually happens is that people will take that model or a existing model, and then they will feed public data to start your training and combine that public data with private data that the company itself owns. And that private data is something that you don't have, or your attacker won't have. But then again, they already have the architecture and a pretty good estimation of the weights because they have the public part. So it's pretty common that people will get to this point. Okay, so scary. To run this part, if you've never run Jupyter, just click the play button. And here the first one is just importing stuff. I already ran this too because the model takes a little bit longer. But here you can see the nice thing for TensorFlow and Keras. In Keras, we can already ask them, hey, give us the image classification model. And we already want it trained. So we want it trained with ImageNet. And that's it. That's what you need to consume a model. And you have a large amount of public models that you can find here. So if you have the time, play around with Keras. That's a pretty good starting point. This particular one is mobile, so it's optimized for the web and for smartphones. So the accuracy is not that high, but it's fast. It's pretty fast. All right, this next block, here we are just declaring two helper functions. And this helper functions is basically just taking our input image and transform it in the metrics that the model can understand. So for the model, you will have a vector of features, like Jaime was telling us. We are just transforming a input image, whatever that might be, into that specific vector of inputs. So yeah, pretty easy. We just tell it that we want vectors. So that's what this resize is. These vectors are floats. And we asked the mobile net to do the transformation for us. So no big deal. The second function is to get the one from the outputs, what the labels are. This network gives you a lot more information, so we are just coding them to get the one that we care for. Right. So here we get our sample image, and this is the same image that Jaime was showing us. It's a Labrador, and this you can just in the image path you can use do a local call, and you can use whatever image you have in your machine. Here we are using get file, so we can get the image from the server. But it's just an image. So remember, when we have an image, we need to transform it. And here we are showing we are transforming it back into an image and showing the label that the model thinks it is. Right, so it's the same example that we already seen. It's a dog, and it tells you it's a dog. And I'm almost sure that it's a dog. Oh. So now the fun part: how do we create these noisy images? Right. So what we want here is just the sign. So like the method said, it's just using the sign, and it's everything. That's pretty much everything you care for. The thing here is that you need to know what your training weights are, and this is this part. So to optimize things, TensorFlow doesn't save the whole training process. Since we are using gradient descent, it just saves the gradients, and it uses kind of a queue. So here we are asking it for that for those weights, and we give it the image, and we watch those weights and get the gradients from there. So white box totally, right? You need to know exactly what's happening inside your model. And here we actually use that. So here, these first 3 lines is just decoding what the images are in the outputs, so we can actually see them. And here we can see that we are just creating the adversarial pattern and showing this pattern. So this is the noise that we are going to be introducing, and that's our adversarial pattern. And here we already have our perturbation. We already have this noise. We already have our image. Now everything that we're gonna be doing is just to our image adding this noise with an epsilon. And this epsilon, Jaime already told you, it's a very small number. So here you can see no epsilon, that will be your original, 0.01, 0.1, 0.15. Right, so as epsilon grows, you're gonna see that your image is getting noisier and noisier, and also the classification is getting worse and worse. So you, as an attacker, you will need to find the right balance between the noise that you're introducing, but not so much noise as into somebody actually noticing it. But this is our original image. Remember, this is the same percentage of confidence that we got before. With 0.01, we can see that it's pretty much the same image, but now it's not a dog. It's confusing it for something else. And here we increase more to this epsilon. Here now we can begin to see that it's actually pretty noisy, this image. And it's already given us a different classification. Keep in mind that we are showing the top classification so pretty much what this means is that the network doesn't know what this is. And the thing it resembles the most is this Waymeter, whatever that is. But it's just 15% confident that it's actually that. So here you can see we added a larger epsilon and we almost got no difference, but the image is pretty noisy. So that's how you will find that above this threshold, it doesn't really matter if we keep increasing our epsilons. But if we keep increasing epsilons, then it's most likely that somebody's going to find out that this is an adversarial image. And that's it for this demo. As you can see, it's pretty easy. It's just some functions to transform to our images. So most of it is just image handling. And what we are really doing is getting the signs for the gradients to generate this noise. And we basically just our image plus that noise plus times our epsilon. And that's that. That's how you generate an image, and that's how you will generate a noisy example in whatever network you're using. Do you guys have questions here? Well, I'm gonna stop sharing to give control back to Maddie, Dr. Maddie. But if you have questions, feel free to ask those in the chat or something.
Okay, thank you, Edgar. Let me just conclude. Do you see my screen?
Yes.
Okay. So basically, yeah, it was a short workshop. Okay. So what we discussed and what we observed is like we discussed what is adversarial attack, why it is important to know about it, why it's important to understand how it works, why, and we also saw when it happened and how it happens. Then we talked about basically Jaime talked about how to defend against it, and also we had a hand-on experience by the help of Edgar. So actually, to summarize, basically we can summarize this like there are many shortcomings in machine learnings, and of course, these shortcomings can have a large impact in real life. So those are basically need to be addressed by machine learning community, and I mean, people there are tons. There are so many researchers that are working on addressing those shortcomings and improving, basically making it more secure, so it won't be like that easily, basically misleaded the applications. So by this slide, actually, I basically conclude this workshop. There are certain sources here. Our contact emails are here. You can contact us if you have further questions. These are basically the package that it was using. This is a very useful survey articles that I invite you to read about it if you want to get more information and a better basically knowledge about it. And also you can, in this blog, you can get much more basically information in this regards. So actually now I want to open basically the floor for a question and answer if there is any questions, so I can try to address them.
Hola, hola, ¿hay alguien que quiera hacer alguna pregunta?
You can text if you don't want to say it out loud. You can still put it in the chat. I mean, if there is questions. I think there is no questions or doubt. Anyway, these are our contact. You just write them down. If you have any further question later on, you had some doubts, maybe you basically went through the slides once more and you had some questions, feel free to contact us at any time. And thank you for your time participating. I hope you learned something. I mean, something new at least. Okay. So yeah, that's it. I don't know if Abby, you want to add something?
No, thank you, Maddie. Thank you, Jaime and Edgar. I think it was a really good session. And if anyone has any doubts, there is their contact, or you can reach out for us in our social medias, or I don't know, via our mail that I have sent you some mails previously, so you can chat with us there. And thank you very much for your assisting.
Thank you. Thank you so much.
See you soon.
See you. Bye.
Thank you. And see you.
Thank you.